Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a theoretical physicist currently doing a postdoc at the Helsinki Institute of Physics over in the University of Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how things evolve, how things interact, all of the cool things happening inside the universe. It's great fun. I love being a physicist, I love being a cosmologist, and I love chatting to everybody about all of the cool things I get to work on, all of the cool things happening in space, in the universe, everything like that. I don't work on everything, of course, although sometimes I feel like I do. I just work on some things, and I'm happy to talk about anything you want to talk about. For anyone who's new here, this is an interactive stream. The idea here is that you people can ask me anything you want about space, about physics, about cosmology. Some of those are interchangeable terms. About life in Finland, about academia, basically anything you want. You can ask me questions. I will do my best to try to answer, or just completely ignore you if I don't know the answer, and then I'll always just give a hand-wavy argument or say I don't know. So if you're a first-time viewer, or if you're a regular who hasn't done so yet, please do like, subscribe, leave a comment down below, do all of the usual YouTube things. You all know how YouTube works. Press buttons, make stuff happen. It really does help. I really appreciate everyone who leaves comments and likes the streams and everything. It's always extremely useful. So please do all the things that you normally do, subscribe, leave comment, ring the notification bell, blah, blah, blah. You all know the stuff. So hello to everyone joining in the comments. I see a bunch of regulars. I see some people that are always here. It's good to see everyone. Hello to Mito. I see Ange here. Paul, great to have you back. Missed you the last couple of weeks. Great to see you again. David Howden, Kimmer, James, great to see you all coming in. This is my bad arm. So in answer to the question of how is my arm doing, it is better. I can give more hand-wavy explanations, but this arm is still slightly unusable. For people who didn't hear last week, 2 weeks ago, I slipped on the ice in Finland. Apparently, walking on ice is extremely precarious. I ended up in the emergency room, thought I damaged my elbow. I did damage it, but nothing broken, just very painful arm that still hasn't fully recovered, but it is definitely improving. So I can definitely use it a bit more, but in general, I'm trying not to use my right arm too much, but I can do plenty of hand-wavy explanations with one hand. Don't need to be hand-wavy. I mean, it's better with two, but don't need to. Okay, so good evening to everyone, good afternoon, good morning, wherever you are in the world. Someone saying you like the Celestial shirt. Thank you, me too. And I just need to show off how awesome this shirt is. This is my ugly space shirt. It is so ugly, I love it. Secondhand. A friend saw this in a secondhand shop and sent a photo like, who would wear this? I was like, me, I want it. I love it, and I get to wear my work on my shirt. It's very cool. It's a very cozy jumper, and it's very spacey, and I love it. And yeah, it's very cozy. I'm glad people pointed it out. I'm not sure if this is the first stream where I've worn this space jumper, but now it's my thing. When I'm giving talks, I'm just wearing my space jumper, because why wouldn't I wear my space jumper? It's a very cool space jumper. I last week, I think you all saw me in my hideous Christmas jumper, which is more hideous than this one, but also absolutely amazing. I found a button that makes you appear on my TV, so I pressed it. Oh, that's cool. Yeah, put me on TV screens. Why not? Put me on whatever screen is the best for you to watch me on. I know sometimes on the phone it can be a bit small, so if there's a button that puts me on TV, go ahead, do that. Yeah, press those buttons, see what happens. If in doubt, just press buttons. Right? Anytime you see a random button, just press it and see what happens. Please don't quote me on this. Please don't get in trouble pressing random buttons. But yeah, buttons are meant to be pressed. It's like when you board a plane and there's all those buttons next to you that control the gangway, and you're very much not allowed to touch them, but big fancy red buttons. Anyway, do not let me near any big red buttons, because I will try to press all of them. Yes, this is incidentally when you're on a treadmill and there's this big button that says stop, and it's just a temptation to press that button so many times. Anyway, a word of advice, don't do that. It slams on the brakes. It's very spectacular. It's not worth doing. Okay. So, I don't like For All Mankind for the name, but you really have to watch it. This week's episode was especially wonderful. I have heard a lot of very, very good things about For All Mankind, and it is actually on my watch list. It's been recommended by quite a few people now, and it is on my watch list. So I plan on getting to For All of Mankind at some point. The problem is there's quite a few things on this watch list. And For All of Mankind, I think, is on Apple TV, which I don't currently have. So I don't currently have access to For All of Mankind. But I have heard good things about it, so it is on my watch list. My watch list was overtaken the last week by doing a rewatch of the complete Lord of the Rings trilogy, which obviously took a long time because it's like more than 9 hours of TV to watch. So that's been keeping me busy for a while. But now that I finished that rewatch, I will move on to other things. And For All Mankind is definitely on my list. Okay, great to see everyone here. If there's anyone I didn't say hello to, sorry. I think I said hello to everyone. the other David Dunton, say hello to you. Great to see you here as well. Great to see everybody as usual. Doctor Who is brilliant. Absolutely agree. I've watched all 3 of the specials. We're going to keep this a spoiler-free zone. Please do not put any spoilers in the comments for those who haven't had time to watch it. But I really recommend watching the 3 specials of Doctor Who. With it's just really, really cool. So very much worth watching. Basic question: in the percentage of what the universe is made of, is light considered part of the 5%? And is light considered energy? I love these questions. These are very cool questions. And yes, let's get into some actual physics. Okay, so I'm just going to bring up my picture of the components of the universe. So this is actually a great question to get started on, because I always say, everything you see in the universe, the stars, us, my coffee mug, everything that you're used to is normal matter. And normal matter is only 4.9% of the energy budget of the observable universe. Then there's 26.2% that is in the form of dark matter. So dark matter is this weird type of matter that interacts via the gravitational force, but doesn't interact via the electromagnetic force. This means that we cannot see dark matter. As far as light is concerned, dark matter is invisible. Realize I started speaking extremely quickly today, which is not out of character for me, but I should remember to, drink, calm down, and not speak too quickly. Okay, and I'm going to move that over there before I pick it up with the wrong arm, because that is heavy and that hurts my arm still. 26.2% in the form of dark matter. Dark matter, invisible thing, doesn't interact with light, but does interact gravitationally. And then we have the 68.9% in the form of dark energy. Now, dark energy is this weird type of energy that is driving the accelerated expansion of the universe, and that's pretty much everything we know about dark energy. It's pushing everything outwards. And these percentages are today. So these percentages have been different at different points in the time. This is going into what Paul is saying here. Does the percent of dark energy grow as the universe expands? Yes, it does. So these are the percentages today. But if you did the same snapshot of the universe right after, for an example, the time of the CMB, you would mainly see CMB. No, that's a bit too late. Earlier than that. Yes, a bit earlier than that. At some point, you would see it mostly dominated by dark matter. At some point, you would see it mostly dominated by photons, which are radiation. So going back to the other question here, of the original question that I've already lost in the comments by James here, of is the percentage of the where is light in this picture? So light is part of normal matter. When we say normal matter, we mean everything that is within the standard model of particle physics. So this includes the usual fermions, the bosons, the quarks, the leptons, everything there together. So like protons, they're not part of the standard model, but they're made up of standard model particles. And photons, particles of light. So particles of light are considered here in the normal matter component. So even though we think that light might be energy, light is actually made up of a continuum of particles. All of these or quanta of particles. All of these particles have an associated energy to them. Everything has an associated energy to them. And this behaves like radiation, so it behaves like a massless particle, basically. But it does have energy associated to it, but it is not energy by itself. It is a particle that carries some energy or some information with it. So all of the photons, all of the particles of light that you see in the universe are part of the 5% of dark matter, 5% of normal matter, 5% of normal matter. And then going back to what Paul was just saying about how does this change throughout the history of the universe and so on, right after the end of inflation, or not long in the early universe, like 3 minutes after the end of inflation, the universe is made up mainly of photons, these particles of light that have come about from the interaction, from the matter and antimatter annihilating. This produces a bath of photons. So in the early universe, you have a lot of photons, you have a lot of neutrinos. Then as the universe expands, these different components behave differently as the universe expands. So they dilute differently. So radiation dilutes faster than dark matter, than dark energy. So as these dilute differently throughout the universe, as the universe expands, they can shift in which one is more dominant. So in the very, very, very early universe, we had what is known as radiation domination. During radiation domination, the universe is dominated by radiation in the form of photons, particles of light, and neutrinos. Then as the universe expands, dark matter becomes the main component. Dark matter is still what we know it is today. And then later on in the history of the universe, we reach matter-dark energy equality. After that, dark energy becomes dominant. And then we say we've entered the dark energy dominated era of the universe, which is what we're in today. You can add another epoch in the very, very, very early universe, which we call like the inflationary period, where the universe is dominated by inflation. But this is still, there's a lot we don't know about inflation. So we have the radiation epoch, where photons and neutrinos dominate. Then we have dark matter, where dark matter or matter-dominated era, where matter dominates, and because dark matter accounts for 80% of it, we say dark matter dominates, and then dark energy dominates. So we have these different epochs in the history of the universe. And they change when you reach equality. So at some point you have radiation matter equality, and then matter dominates. Then you have matter dark energy equality, and then dark energy dominates. So yeah, there are these distinct phases, and when we talk about this picture today, photons are included in the normal matter part. I say normal matter because it's only like 5% of the universe, but it is the one we are used to. So the 5% includes radiation, and then includes photons. And then there's the interesting question, going back to this picture, of where do you put neutrinos? Because neutrinos are part of the standard model of particle physics, but neutrinos have the fun thing that they travel almost at the speed of light. They do not interact electromagnetically, but they do interact gravitationally. So neutrinos kind of sound a lot like dark matter. However, we can calculate how many neutrinos are in the universe, and it's a lot, but it's also an almost insignificant percentage of the universe. So if we were to put it in this pie chart, it would be, I think it's 0.1%, 0.01%, something like that. It's like a ridiculously small fraction, doesn't even appear here. But neutrinos behave a lot like dark matter. So then some people ask the question of, can neutrinos be all of the dark matter? But as I just said, we know how many neutrinos there are in the universe, and there's not actually enough. So there wouldn't be enough for neutrinos to be all of the dark matter. And if neutrinos were more abundant, if we had more neutrinos, we wouldn't have as many galaxies, because neutrinos would prevent galaxies from forming. They wouldn't allow things to fall down and cluster because they travel too quickly. So we know that neutrinos do not account for, there aren't enough neutrinos in the universe to be dark matter, and if there were more neutrinos, we would see this based on how galaxies look. So then the question is, where do we put neutrinos? And this very much depends. You can either put neutrinos in with the dark matter, because you can say they behave like dark matter, but commonly, because it's not enough anyway, then you need another dark matter explanation anyway. So it's more common to group the neutrinos together with the normal matter as well. So the 4.9% normal matter includes neutrinos and photons. Both of these count as radiation. Then we have 26.2% of dark matter, and the rest in dark energy. Question here from Prath. I've seen the one from Paul. I'll go back to that in a sec. There was a time when there was less dark matter energy than normal matter. Not so much less, but because these are counted over like so the way we count these energies are relative to the size of the universe. So this is always the like relative fraction. This is why it adds up to 1, right? Because we're counting everything inside the universe normalized to a universe that is flat, and this gives us the critical density. If the universe weren't flat, you'd have another component here that would be the energy density and curvature. And then you'd have another thing, but this is an energy density. So because it's an energy density, it's kind of normalized, or it changes based on the volume of the observable universe. So all of these are the numbers today. If we go back to the very early universe, then relative to the volume, there would be other ones that have more dominance, just based on the size of the universe. And then so right after the end of inflation, you have a lot more photons and neutrinos per volume element than anything else. Then as the universe expands and these species are diluted away, the way they're diluted away throughout the universe is different. So the radiation can move around very quickly, whereas the dark matter, the dark energy take different amounts of time to move about. The way they expand in space is different. You can calculate it relative to the scale factor, which gives you the expansion rate, so to speak, and then you get different ways that they depend on the scale factor. So it's not that there was more matter than dark matter or more dark matter than dark energy. It's just when you calculate their overall energy densities relative to that point in the history of the universe, you get different ones being more or less dominant. Hope that makes sense. If not, let me know and we can go through that again, because it's quite hard to wrap your mind around how these different species expand and dilute throughout the universe that is also expanding. So It's kind of tricky to get these percentages. I'll actually at some point add another chart. Yes, I went to drink water and stopped. I'll add another chart to here about how this looked like in the very early universe, because there are people who put the two pie charts side by side, like this is what it looked like, but then this is what it looks like today. So it's quite cool to do that as well. Okay, so I'm not ignoring your question, Paul. I will come back to that in a sec, but another question about this pie chart. So I'm going to stick on the pie chart before we moved onto the other questions. Where would gravity fit into this pie chart? Is it apples and oranges? Somewhat. So gravity is one of the four forces. The universe as we know it is governed by four forces. There's a gravitational force. I drop pen falls down. This is gravity, this is gravity, this is what we're used to, this is what we know. I drop pen falls down. We stay in orbit around the sun. Gravitational force. Cool. Next force is the electromagnetic one. I turn on a light, there's light. I pin a fridge magnets. We know how electricity and magnetism works. Then there's a strong force responsible for holding things together at the atomic scale, and the weak force, which is responsible for radioactive decay. So these are four forces. So they're not so much the building blocks of the universe. They tell us how these building blocks can fit together, what you're allowed to connect with what. So the forces don't really contribute to the energy budget of the universe. However, three of these forces are carried by specific particles. Gravity, let's just ignore gravity for now because we don't know what gravity is doing. But the other three are carried by specific particles. So photons carry the electromagnetic field, the W and Z bosons carry the weak force, and the gluons carry the strong force, and these particles are part of the normal matter. So the mediators, the particles responsible for carrying these forces, are part of normal matter, but the forces themselves are not, because they're not a component of the universe. They're the rules that the universe plays by, we think. Gravity doesn't fit into this because, again, it's kind of one of the rules that the universe plays by, to our knowledge, are not an actual component inside the universe. If we ever discover gravitons would be the particle that carries the gravitational force. This would then fit somehow into the standard model. We think, we haven't figured out how to do this, and then they would also be part of normal matter. We don't expect gravitons to account for dark energy unless you're looking at alternative theories to gravity, where instead of some modified gravity theories, where instead of having dark energy, you try to explain all of the effects of dark energy with modified gravity. Finding gravitons would be interesting because it's something very much associated to the gravitational force, and therefore it would help us understand a lot of things about gravity. However, we have not figured out if a graviton can even make sense, because we really don't know how to connect the gravitational world, the gravitational force, which describes the macroscopic world, with the other particles that describe the quantum world. To do this, we would need a theory of quantum gravity. If anyone has a spare one of those lying around, please do let me know. But for now, we haven't found a convincing theory of quantum gravity that is able to put these things together. So I think I just answered another question there about gravitons, and there are still some questions that I know I didn't answer, so I do want to go back to that. But sticking with this, okay, no, that's a question about the Higgs field, so that will come later. I'm going to go back to Paul's question here. You will have some very, very cool questions today. I love that when we get on these topics, we can talk about a lot of different things, and these questions are all very connected, so it's nice when we can stay on topic for a while. But I think that was those related to that. Okay, let me just recheck. Okay, question from Paul. Are there credible dark matter theories where the dark matter interacts with itself with a set of forces other than gravity, even if it doesn't interact with normal matter? Yes, there are. I love this question. Excellent question. And I like that you added the word credible theory, because there's a lot of dark matter models, and some make more or less sense, and some are more or less compatible with the data. Now, I would hold off on calling any of these things dark matter theories, because we don't really have enough evidence or data to call any dark matter model a theory, because a theory would imply that we've actually found, that's made predictions that we've been able to observe. The theory is the gold star of physics, of science in general. So there's a lot of dark matter models. And your question about can we have dark matter models that interact with something else, like with themselves? There is something known as self-interacting dark matter. As the name implies, this is dark matter that interacts with itself. The way it interacts would be via a new force that only exists in the dark sector, so like with dark matter. And this type of interaction it's actually really cool because it might help us explain, for an example, why there aren't as many galaxies as we expected on specific distances, or why it looks like dark matter always behaves the same inside galaxies instead of behaving slightly different. These are things that we're not completely sure how to explain. And there was this idea of self-interacting dark matter, where dark matter could interact with itself via some type of force in the dark sector. And this would lead to dark matter kind of binding together in a way. This would be a very cool idea. This is a model that has been discussed a lot. The kind of ways you could go about looking for this is looking at how structure forms on cosmological scales. So the cool thing about self-interacting dark matter is it kind of bridges particle physics and cosmology, because you can come up with self-interacting dark matter models from a particle physics perspective. And then you can use cosmological observations to study these. So that's very cool. And then there's also, sounds like it could form molecules and other structures. You beat me to exactly what I was about to say there, Paul. And also was going to be atomic dark matter. So, within the standard model of particle physics, we know there are 4 forces. And we know that normal matter, standard model, and all this is only 5%. Dark matter is 26% of the energy budget of the observable universe. Then we can ask the question of, could there be a rich dark sector? Why would we expect dark matter to be one thing when the standard model is not one thing? Could dark matter be composed of many different types of dark matter that have different interactions? Could you have, for an example, dark light? So similar to the electromagnetic force, but in the dark sector. And how would this work? And then you can have some massless dark particle that we would call either dark radiation or dark photon, depending on how you build this from a particle physics perspective, that would behave very similar to light, but in the dark sector. And if you have, I keep using it, and you can tell when it hurts. So if you have more than one type of dark matter, could you also then form dark nuclei and have a kind of a dark electron equivalent, not an exact replica, but the equivalent, and then could you form atomic dark matter? And a lot of people have looked into these things, myself included. I worked on these types of things, the dark radiation one during my PhD, and in my first postdoc a bit as well. They are very cool. Now, the problem, the usual argument that you get here is like, okay, before we start looking for 50 types of dark matter, let's start looking for one, right? We have to find one before we can find the other 50. But there are a lot of models. Now, the problem is, depending on how you build these from a particle physics perspective, you might then have interactions with the standard model, because depending on how you build these forces, they might kind of bleed over into the normal visible sector. So that would leave signatures. One way that people look for an example for atomic matter is using, you can probably all guess what I'm about to show, but one way you can look for atomic matter, come on, my slide deck is being disagreeable. One way you can look for atomic matter is, of course, using the CMB. It took me over 20 minutes today. That's got to be a new record. Because if you have some type of atomic matter, you might have some type of photons being produced by this atomic dark matter in the same way that photons scatter off of normal particles. They could also scatter off of atomic dark matter. Dark light, you have to love the oxymoronic name. It's literally called dark light. I love it. It's very cool that we call it that. But if you have some type of atomic matter, this could actually affect the energy of the cosmic microwave background radiation. This map here is the CMB, cosmic microwave background radiation. This is the oldest light we can see in the universe. It's a background in any direction we look. And it's a snapshot of what the universe looked like 380,000 years after the end of inflation, after the Big Bang. What this is showing us is the temperature differences. So this background of photons is at more or less 2.73 degree Kelvin, but there are tiny, tiny, tiny variations in 1 part in 10,000, 1 part in 100,000, sorry. So some of these photons, particles of light, are slightly colder, some are slightly warmer, slightly hotter, and when you take them together, you get this amazing map of what the universe looked like. Now, this map gives us the statistical properties of this baby universe. By looking at this map here, we can figure out what the baby universe looked like, how much dark matter there was. These numbers I gave you before, the ones that were in this pie chart, if it's going to load, these, come on, slides are a bit slow today. These numbers here, the 4.9%, 26.2%, 68.9%, these come from the CMB, the cosmic microwave background radiation. So Some people have tried to look for atomic dark matter signatures in the CMB. And it's pretty cool because once you've built this kind of complex dark matter sector, there's a lot you can play about with. And then here you can say, like, okay, can atomic dark matter, if it exists, how would it impact the CMB, if at all? And if we then make atomic dark matter have decays and interactions the same as normal dark matter does, how big can you go? Can you build dark matter nuggets? And then you can lead into another dark matter model known as dark matter nuggets, where you literally have little nuggets of dark matter. And this is very cool. Now, the problem is that if you want to form bigger and bigger dark matter structures, then you run into things like the bigger dark matter structures you would see with different lensing experiments. So then you can put limits. There's some ideas. For an example, there's a model that I love, which is called MACHOS, and that stands for massively compact halo objects. Yes. And MACHOS are often considered an alternative to WIMPs because physicists' names, blah, 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 so bad at it. So WIMPs, weakly interacting massive particles, are the standard dark matter candidates, where dark matter is a particle. MACHOS, on the other hand, would be these big, like dark matter is made up of planet-sized chunks. Now, the problem with MACHOS is that then lensing kind of puts heavy constraints in it, but you can get away with this. Then you can tie that directly into primordial black holes. So if you think of a black hole, the standard picture we have is a star that's reached the end of its lifetime and collapsed and formed into a black hole. But, it explodes in a massive supernova, and the remnant that's left behind is a black hole. Yes, MACHOS versus WIMPs, literally, these are the names of these things because physicists. Yes, so primordial black holes, on the other hand, as opposed to going through the whole stellar formation process and collapse, primordial black holes are black holes that could have formed in the very, very, very early universe, where there's regions of the universe that are so dense that they can directly collapse to form black holes. These primordial black holes would behave very, very similar to the MACHOS that we mentioned before, just with different formation things. You can say primordial black holes are MACHOS that were formed in the early universe, whereas you could have MACHOS that are formed today. So this is the thing, that you can have some type of constraints, but there are plenty of models. So I just did a whirlwind review here of a few different dark matter models. We started with self-interacting dark matter, so dark matter that has interactions with itself. From here, you can build more complicated dark matter models like atomic dark matter. If you have a lot of dark matter clustering together, could you form dark matter nuggets? What if you have planet-sized dark matter chunks? Then you have MACHOS, and if these were formed in the very early universe, you have primordial black holes. These are 5 candidates that I just brushed through, and WIMPs, weakly interacting massive particles, the standard one. So these are 6 candidates I just brushed through in 5 minutes out of literally thousands of dark matter candidates and options that we have. And Paul, your question was specifically, are there credible dark matter things? I know I went very off from the self-interactions because the self-interactions were only the first one. The other ones, you don't necessarily, like MACHOS and primordial black holes, you don't actually need any forces beyond what we already have in the standard model, and then you just use gravity to attract these objects. So the question was, can we have self-interacting dark matter? The short answer is yes, potentially. The long answer, just gave that one. But you also don't need self-interactions to form bigger structures like primordial black holes or MACHOS. Some of these leave signatures in things like the CMB. When I say signatures, I just mean some type of like imprint that we might be able to measure. Some of them have impact on the CMB, some of them have impact on lensing experiments. Ideally, we take all of these different data sets, we put them together, and we gradually narrow down what dark matter is allowed to do or isn't allowed to do. And this is how someday we might figure out what dark matter is, by first finding out 1,000 things that do not work as dark matter, and then eventually we might find out what does work as dark matter. So thank you for the dark matter questions, because as you can tell, I love dark matter. This is literally what I've been working on since I started my PhD. I'm currently not doing so much in terms of dark matter. I've shifted into gravitational waves, which is an equally fun topic. But I am always happy to go back and talk about dark matter again. Also, you cannot imagine how many new ridiculous puns people come up with in paper titles when working with WIMPs versus MACHOS, or MACHOS by themselves. Then you throw in there's a lot of ways that physicists come up with random puns in their paper titles. Now, personally, I am of the opinion that a paper title should be descriptive. When you read the title, you should know what the paper is about. So what I think is the best possible solution is to find a title that is both descriptive and funny. And if you can do that, it is a great title. But titles that are just funny for the sake of being funny, but then lose the purpose of telling you what the paper's about, I think defeats the point. Like, sometimes people come up with completely random titles that you read and it's like, I literally have no idea what this is about, but it's an amusing title. The paper title that I am proudest of my own is when I was able to sneak a Lord of Rings reference into the title of the paper while still describing what the paper is about. And I'm very proud of that title because it took me a while to come up with, but I managed to get a Lord of the Rings reference in a paper title and still tell you what the paper is about. Love that one. Okay, I know there was another question very early on about Higgs boson that I overlooked, so I'm going to go back to the Higgs boson once I've investigated this deep. Right, the title of my paper is One Likelihood to Bind Them All. Multi-scale constraints on, no, what's the second half? So we developed a new likelihood. A likelihood is a way, I'm just bringing up my paper to give you the exact title. So a likelihood is the way where we build kind of a tool that allows us to compare the data to a model. And we built a likelihood, a set of tools that's, you want to call them naturally compact halo objects, yes, call them naturals instead. And then you can come up with cheese, but I'll tell you that people have already beat you to cosmic spaghetti and cosmic pasta and cosmic lasagna. These are actual things, that are actual scientific names for things. But yes, you can have naturals. Right, so a likelihood is a way of connecting data and models. So for an example, if you build a CMB likelihood, what you're doing is you're building a code that can take CMB data and compare it to your cosmology. So it's the in-between step of comparing data to model. And what I spent a lot of my PhD doing is building likelihoods to use Lyman alpha data. Now, the problem here is that this usually means you build one likelihood for one model because the way you compare the model to the data depends on the specific model when you use Lyman alpha data. So Lyman alpha data is just looking at how hydrogen behaves in between galaxies. So we came up with a method that allows you to have one likelihood and it covers about 20, 30 different dark matter models. So it's pretty cool. It's like this big one likelihood to do a lot of things for you. So what did we call it? We called it, paper title incoming, One Likelihood to Bind Them All, Lyman alpha Constraints on Non-Standard Dark Matter. So what are we doing? We're building a likelihood that gives you Lyman alpha constraints on dark matter. And what do we have? One likelihood to bind them all, and in the darkness will fold them. Well, I know that's not the exact quote, but you get where I'm going with this. So yeah, we had one likelihood to bind them all, Lyman alpha constraints on dark matter. And I'm very proud of this title. So this one, and the pun I made about cannibal dark matter, we wrote a paper about cannibalism in dark matter. That's another dark matter model where dark matter can self-cannibalize. It's a very fun one. So yes, there are a lot of dark matter models, there are a lot of stupid titles and a lot of fun titles and a lot of stupid names and a lot of fun names. It's fun. I literally had a couple of people email me just to say, I read the paper just because of the title you came up with. I was like, thank you, mission accomplished. Now, if I made you laugh and I made you read my paper, excellent. Okay, I just saw something about fuchsia that I had not seen. I need a pie chart of effort in paper writing to see what percentage is spent on working title. Yes. Yes, way too much effort is put in paper titles. I myself am very guilty of this. If you go through my early drafts of papers, there's like 5 different titles every time I come up with a new one until eventually we all agree on one. Yeah, usually way too much time is spent on title and on making your figures look pretty, which I don't think is a bad thing because your paper should communicate the main thing of your paper. And if your figures aren't pretty, people are not going to care because we all like looking at pretty pictures. Okay, let me see. Is there cosmic ravioli? I think there might be actually. There are cosmic pancakes, which are a type of galaxy. Cosmic ravioli, there is a moon that is known as cosmic ravioli. It's a moon of Saturn. But otherwise, no. So there is a cosmic lasagna. Okay, so very long ago, there was a question about Higgs boson. I'm just going to scroll all the way back up and look for the question because I saw something about Higgs and thought I'll come to that in a minute. And then went down on a very long tangent about dark matter, which was a very fun question. Okay, we covered Doctor Who, we covered percentage of light, we covered percentage of dark energy, credible dark matter models, that's the one we just did. Okay, where will gravity fit into this? We did that one. Question from David Howden. Before the Higgs field turned on, did dark matter have mass, even though ordinary matter didn't? I love that question. So, as far as we know, everything in the universe gained its mass via the Higgs boson. So the Higgs boson is the particle responsible for creating the Higgs field, and the Higgs field is the field that is everywhere in space-time, and that gives everything mass. Just so the comment here with wine, the aroma, and the story behind it, and the label that enhance the experience, a paper title does the same. Thank you. Yes, I agree. Once you know the reason behind a paper title, it makes even more sense. Thanks for stopping by, David. Great to have you here, and have a good evening, weekend, rest of the day, and hope to see you next stream, which I don't know yet when that will be. Okay, so Higgs field. Higgs field permeates space-time. It's everywhere in space-time. And you can imagine the Higgs field as being like cosmic maple syrup, or treacle if you prefer, that when particles move through it, they encounter friction. And this friction, or this difficulty to move through it, is what we then interpret as mass. So the Higgs field is everywhere in the universe. You can tell, I'm wondering if people are going to pick up on the theme that I'm hungry, given that I keep talking about like cosmic spaghetti and pancakes and now maple syrup, but I have a snack in the cupboard for after the stream, so it's all good. Finland has amazing seasonal snacks. I'm going on a random tangent here. There are some snacks that are very like calendar dependent in Finland, and at different times of the year you get different snacks. Like around 1st of May, which is a very big holiday here, you get monkeys, which are donuts made with cardamom and coated in sugar, and they are delicious. And then at Easter, which I know is beforehand, you get mammi, which is sweetened rye pudding. It's phrased as an acquired taste. I have not yet acquired a taste for mammi. But there's all these seasonal desserts. And the point being that now we are at the time of the Christmas dessert, which I love, which is joulutörttu. There's a few, but joulutörttu, which is basically a small square of puff pastry folded into a star with a blob of jam in the middle, baked and covered in powdered sugar. It's simple and it is utterly delicious. And I absolutely love them. And you can only get them in November, December. And then as of January, they're gone from the shops. Of course, you could always make your own. So anyway, I have a joulutörttu waiting for me in the kitchen for after this stream. Random tangent there, but I'm very happy about this. Anyway, back to the maple syrup Higgs boson. I heard 2 weeks ago about cosmic pastas in the stars, lasagna, gnocchi, spaghetti, bucatini, yes. Yeah, they find random shapes in their simulation and they say, hey, look, this looks like cosmic lasagna. You also get cosmic lasagna at the center of neutron stars where you compact things together and you end up with different layers, and people are like, hey, this looks like lasagna because we're great at naming things. It's actually a pretty decent tea. Okay, so Higgs boson, treacle, maple syrup in the universe. Even forgotten the question, but right, Higgs boson and dark matter. Yes, that was the question. My mind is jumping about today, even more than it usually does. Okay, so at some point in the early universe, around the time of the electroweak phase transition, which is when the electromagnetic force and the weak forces separate, because when you go to very, very high energies in the universe, the forces were connected. So at some point, we know the electromagnetic force and the weak force were united in the electroweak force. You could then hypothesize that at an earlier time, the strong force was also joined together. If you come up with this, you come up with a grand unified theory. And then if you figure out how to put gravity in the mix, you have a theory of everything. We haven't got the latter two, but we know that the electroweak forces were joined, the electroweak force, and at some point they split apart into electromagnetic and weak force. At this point, you had a phase transition where the universe changed its overall makeup slightly, its overall markup changed. And at this point, the Higgs boson switches on, the Higgs field activates. Once a Higgs field activates, everything in the universe can acquire mass by interacting with the Higgs field. What about dark matter? We have no idea. So did dark matter acquire mass through the Higgs mechanism as well? Was there another mechanism that gave rise to the dark matter mass? It's not completely clear. Now, it would be very logical if the Higgs boson and dark matter interacted. And then you can actually do cool things like come up with a dark Higgs that plays the same role as Higgs, but in the dark sector, going in again to our rich dark sector idea. And then if you have the dark Higgs and the normal Higgs, you can imagine a connection between these that we call a portal. If you've ever played the game Portal, where you shoot a portal in one place and you can traverse it, imagine particles doing something similar, and you form a bridge between the dark Higgs and the normal Higgs. This would actually allow some kind of talking between the dark sector and the normal sector. And this might be detectable someday in collider experiments and in gravitational wave experiments. This is known as the double Higgs model. Cool. So, how does dark matter acquire mass? We have no idea. So we have no idea, but it might be via the Higgs mechanism. It might be via the dark Higgs mechanism. Having the Higgs mechanism would be logical because the Higgs gives everything else mass. But you can come up with a lot of different ways of playing about with the standard model and giving dark matter mass. We know that dark matter has to have mass because else the universe wouldn't look the way it does. Or we find a whole other theory that doesn't include dark matter, which would then have to explain why the universe looks the way it does. So we know that dark matter has mass. We don't know the mass of dark matter. This is the thing. With other particles, you can look at how they interact with the Higgs field. You can do measurements. You can do experiments. You can find their mass. Dark matter, there's 80 orders of magnitude for possible masses of dark matter. Dark matter could be billions of times lighter than an electron, or it could be the size of the mass of our sun, depending if you have particle dark matter or if you have matters. If you have matters, you can have dark matter that has mass of 10 to the 5 solar masses. So that's 10 to the 35. So 1 followed by 35 zeros, 35 zeros, kilos. Or you could have something that is a fraction, infinitesimally small fraction of the electron. It's a broad range. It's a very, very, very broad range. So it's very difficult to know how dark matter acquired its mass. Higgs boson seems like the most logical candidate, but then how does Higgs boson talk to dark matter? Does dark matter feel the Higgs field? Feel the Higgs field? Probably, maybe. Is there a dark Higgs? Dark Higgs sounds badass, I agree. It's cool. It's cool. So yeah, it's I think it's a great question. It's a very difficult one to answer. So maybe the Higgs boson and dark matter interact, maybe they don't. We can answer that once we find dark matter, hopefully. So yes, it's a very, very cool question. I've seen a lot of questions coming in. Does the Higgs boson have an antiparticle that could be dark Higgs? Higgs boson does Higgs boson have an now I'm just blanking on this. I always make a mistake with this one. So let me just check before answering that. Is there an anti-Higgs? Is there an anti-Higgs? There should be, right? Okay. So I don't think the Higgs has an antiparticle by itself because it's a boson, right? Yes. Usually we talk about antiparticles when we're talking about fermions, which are particles that group together, leptons, quarks, these type of thing. But when we're talking about bosons, the ones that carry the force, there's not an antiphoton. So then, but there was an anti-W. Yes. So the bosons generally we don't consider antiparticles. So I think for now we don't have an anti-Higgs, but there are models that look at an anti-Higgs. As to whether the anti-Higgs could be the same as the dark Higgs, usually not, because the way that they behave are different. So antimatter is like matter, except it has opposite charge, and the Higgs doesn't have charge, which is why it doesn't have an antiparticle. There we go. But they could, maybe, in some models. Now I want to bring up my standard model of particle physics to just confirm this thing that I just told you here, and then answer another question as well once the slide deck loads, because I need to get from slide 10 that I'm on currently to slide like 35, and then there's some buffering involved here. Okay, but dark matter, yes, dark matter in general behaves very different to antimatter. So antimatter is like normal matter, except it has opposite charge, whereas dark matter doesn't even feel any type of electromagnetic charge or any type of charge to our knowledge. So even we could have an anti-Higgs, an anti-particle, and that would be very different from having a dark Higgs. But of course, these are a lot of different things you can do with the Higgs boson, playing about from a particle physics perspective to build different models where you have 1, 2, or 3 Higgs or so on. I've seen some other questions that I do want to come back to at some point. Standard model of particle physics. Here you have your standard model. In purple, you have quarks. So the top left are the 6 quarks. These are the ones that bind together to form things like protons and neutrons. Then you have your leptons, electron, muon, tau, and the neutrinos. These can be found freely. Then we have the bosons. Gluon carries a strong force, photon carries the electromagnetic force. W and Z bosons, these are responsible for carrying the weak force. And then top right corner, you have the Higgs boson. Now, the Higgs boson, as you can see here, are the three numbers in the top left. Top one is mass, second one is charge, third one is spin. Higgs boson does not have spin or charge, but the Higgs boson does have mass. So this was a question that just appeared here from Scott. Does Higgs itself have mass? Yes, it does, because it has self-interaction. So you can have Higgs interacting with Higgs. So the Higgs creates this kind of treacle maple syrup field in the universe that everything struggles to move through, and then itself feels this field as well. So the Higgs boson has self-interactions, and therefore it gives itself mass. Based on there were many different ideas for what the mass of the Higgs boson could be, but now we found the Higgs boson at the Large Hadron Collider. It's one of the biggest achievements of the Large Hadron Collider, the particle collider in Switzerland, or underneath Geneva, Switzerland and France, that is smashing particles together. And it's kind of a Higgs factory at this point, in that it's producing a lot of, you smash particles together at high enough energies, you can get a lot of particles out. And this is how we're producing a lot of Higgs bosons, and then we can study it. And we know that the Higgs boson has a mass of 126 GeV. This is extremely interesting, because this tells us that the electroweak phase transition, this thing of where the force is separated, was very smooth. If the Higgs boson had a different mass, then there could be the possibility that this kind of phase transition would be bubbly. And if it's bubbly, then you could get gravitational waves, which means if we ever find gravitational waves coming from an early universe phase transition, we could say something beyond what we expect. So that would be cool. And that's what I'm working on. Tangent. Back on topic. Scalar fields do have antiparticles if they are complex, if I remember well. I'm going to say yes to that, but I would have to check that. What about anti-dark matter? Yes, you can have anti-dark matter. There was the whole question in the field. I know there's a Hubble tension question as well. I will get to that in a minute. What about anti-dark matter? So, can dark matter have an antiparticle? Is dark matter its own antiparticle? What's happening with dark matter antiparticles? Yes, dark matter could have antiparticles. But then it's even harder to find, right? Because already finding dark matter is hard. And then you want us to find anti-dark matter as well. This is a bucket there. But then there's a cool question, and actually one way that we search for dark matter. If dark matter is its own antiparticle, so dark matter and anti-dark matter could annihilate, these could actually they could create standard model particles. For an example, antiprotons. If you smash matter and dark matter together, you could produce antiprotons, which means one of the ways we search for dark matter is by searching for more normal matter than we expect in specific patches of the universe. For an example, this is what we call indirect detection of dark matter, where you take dark matter, you smash it together, so dark matter and anti-dark matter, or you hope this has happened somewhere in the universe, and then you try to count what you see. With antiprotons, it's especially useful because we know what things in the universe produce antiprotons. Things like tiny pulsars, stars spinning very quickly with a light beam. These can produce antiprotons, but we have an idea of how many. So then we look in a patch of the galaxy, or patch of the night sky, and we measure how many antiprotons we get. And then you check, okay, I expect this many from millisecond pulsars and from other things. How much do I find? We've actually found slightly more than we expected. There's this antiproton excess. Some people say that this antiproton excess points to dark matter interactions, dark matter and anti-dark matter smashing together. However, it could also be that we've misunderstood pulsars, or that there's something else in the universe producing antiprotons. So there's a lot of different things that could produce antiprotons, and we're not sure enough about all of this to say it's definitely dark matter, but there is this hint of there's more antiprotons than we expect, and one possible explanation is dark matter particles smashing together. So that is exactly one of the ways that we try to search for dark matter, and it's pretty cool that we've come up with this idea. And because I'm at this point in the slide deck, I'm going to show you the different ways we try to search for dark matter. So there are three main ways we search for dark matter. These are known as collider searches, direct detection or indirect detection, or the more fun way, the make it, shake it, break it approach. So you can make dark matter if you assume that dark matter and standard model particles can smash together. And then you can make dark matter like this. This is what we try to do in colliders. So I know you smash together standard model particles and you get dark matter out. So we're going right to left here. So you have two standard model particles, you smash them together. You smash them together at high enough energies, maybe dark matter will come out. This is the right to left trajectory here. This is what we do at places like the Large Hadron Collider. This is also how we produce Higgs bosons. Direct detection, you shake it, you have standard model dark matter, these interact, and standard model and dark matter comes out. So we go bottom to top here. What this means is that you create a big, huge tank of, for an example, xenon, and then you hope that enough dark matter hits the Earth that eventually this dark matter is going to shake the existing normal matter slightly, and you will pick up this slight shaking. So this is saying if I have a big enough tank, at some point there is going to be some type of gravitational interaction between the dark matter and the particles. And then you have the third approach, the break it approach. This is the one where you go left to right in this diagram. This is where you assume that dark matter and anti-dark matter annihilate, produce standard model particles, and we look for the signatures or the residue of this. This is indirect because you don't look for dark matter itself. You look for the after effects of dark matter smashing together. I am not sure who initially came up with the make it, break it, make it, shake it, break it. It's something that I heard at first during my PhD. It's become kind of a thing in the field that a lot of people refer to it as a make it, shake it, break it because it's memorable, it's easy, and then you remember the different strategies. I'm not sure who came up with this idea initially, but I feel like it's just been around for a long time, the make it, break it, shake it. The first time I heard it was in a presentation and someone explained it like that, and I was like, oh wow, that was an excellent way of making me remember the make it, break it, shake it. This diagram that I just showed you, I made. So all of the images I show on screen, unless they have credits, I've made them myself. So this one that I just showed here, the sketch, this is my own. So any image that I show here is either credited or is my own. I like that I threw out this comment of gravitational waves, phase transitions, just gives you some bait and nobody took it. That's fine. We have enough other things to talk about. You probably don't want to get me started on gravitational waves 6 minutes or 7 minutes before the end of the stream, because then we'll be here all night. And there's plenty of other streams I've done purely on gravitational waves, so there will be time for that. Okay. To the Sitter Space saying you love me, thank you. You know, I'm glad you're here and enjoying the stream, and it's cool username because the Sitter Spaces are cool. I do like anti-de Sitter Spaces as well. I think all spaces in the universe are cool, but Sitter, anti-de Sitter, very fun. Okay, did I do any follow-up research about muonium? So I did exactly the thing that I said I was going to do. I wrote down the 2 questions last week on my piece of paper. I forgot about the existence of this piece of paper until 15 minutes before the stream today when I took out this piece of paper. And then I was like, oh, these are 2 things I have to look up. I did look up the question of why do forces stop. As to muonium, I got as far as it's a particle made up of a muon and a positron. And it was discovered in the 1960s. And I was like, okay, I'll get back to this some other day. So that's an answer to the muonium question, yes, but also no. I looked into it, but not in a meaningful way. Okay, question from Paul. Are the Hubble tension crisis and the age of the universe doubts from JWST the same issue or related or 2 unrelated issues? Love this question. Thank you. So the JWST, the Just Wonderful Space Telescope, is taking pictures of galaxies and looking for the oldest galaxies it can find. And there's a cool thing that it seems to be finding galaxies that are a bit older than we expected. Galaxies that would imply that the universe is older than we think it is. This is very cool. This is something that also requires a lot of checking and confirmation because doing this type of study is very messy. There's a lot of stuff between us and these galaxies that can affect the interpretation of these results. So while it might look like JWST has found galaxies that are older than expected, there's still a lot of unknowns and uncertainties at this point, a lot of things that we need to figure out. But it is exciting that it looks like it's finding galaxies that are older than we expected possible based on the age of the universe. You know, if I tell you that the universe is 10 years old and then we find a sun or a star that is 4 billion years old, then you're like, you know, how? And this seems to be what JWST is doing. We think the universe is 14 billion years old and it's finding galaxies that shouldn't have been around at that point. The Hubble tension, on the other hand, is the discrepancy in how fast the universe is expanding. So the rate, we know the universe is expanding. We know this expansion is faster today than it was in the past. But then there's the question of how fast is the universe expanding? And we're not actually sure. Well, we think we know, but also maybe not. Because depending on how you do this measurement, you get different answers. For an example, one way you can measure the expansion rate of the universe is by using the cosmic microwave background radiation. The cosmic microwave background radiation, all this light in the universe. From this, you can get the standard cosmological model. You get the parameters that we know of the amount of dark matter, amount of dark energy, and so on. And then you can use everything we get from the CMB as a starting point. You fast forward this and you ask the question of, based on the CMB and assuming the standard evolution of the universe based on our standard model of cosmology, how fast is the universe expanding? And if you do this, you get an answer of about 67.5. Great. Then you can also look at close by galaxies. You look at supernovas, so stars exploding in close by galaxies. You can use these as a ruler to measure distances. And if you measure enough of these, you can get an idea of how fast things are moving away, which gives you an idea of how fast the universe is expanding. This is called using standard candles or local measurement. And if you do this, then you get a value of 73.2. And you might think this sounds good. 67.5, 73.2, they're close. At least it's not 1 and 5 million or 1 and minus 10. That would be weird. They're close, but they're not close enough. Because both of these are extremely precise measurements. So it's not just 67.5, it's 67.5 plus minus 0.5, which means it's somewhere between 67 and 68. And the other one is 73.1 plus minus 1, which means it's somewhere between 72 and 74. These don't overlap, and if they don't overlap, it's a problem. And this is the thing that is known as the Hubble tension or the Hubble crisis, because there is a 5 sigma difference between these. 5 sigma means that statistically, this is a 1 in many, many billion chance that this is a fluke, that this was an accident, that these are the same value, that just something went wrong. So something clearly did go wrong. Either the way we do one of the two measurements is wrong, or the model that we use is wrong, or the assumptions that go into it is wrong. We have not yet found a convincing explanation to resolve this tension, because when you try to solve it, you mess up other things in the universe. So we have the Hubble tension, which is about the rate of expansion of the universe. And then we have the fact that the JWST seems to be finding galaxies that are older than we expect. And the question is, are these related? Maybe not necessarily. So when we talk about the expansion rate of the universe, of course, you could turn that backwards to ask the question of how long has the universe been expanding, and then you get an approximate age of the universe. So you can relate the expansion rate of the universe to the age of the universe, but it's not a one-to-one conversion. There's a lot of things that go into this, right? So they're kind of answering different questions. And while you can find a model that solves the Hubble tension and increases the age of the universe or decreases the age of the universe, it will make other things worse. So it's usually quite hard to put these things together in a way where you can explain both of these at the same time. But I can assure you people are trying. In the same way that we have a few other tensions, a few other minor discrepancies in different data sets. And if you could find one explanation for all of these, like one solution to all the tensions, one solution to bind them all, that would be really cool. So people are definitely trying, but I don't think there's a clear one-to-one relationship between these two problems. They are both very, very interesting. I think for me personally, I think the Hubble tension is a lot more relevant because it's at like 5 sigma and it's really, really a thing that we need to solve. Whereas the JWST measurement of the age of the universe is still in early phases. So I feel like it's perhaps where the other one was 10 years ago. So it's very, very interesting, but it's something that people are looking into. It seems like the Hubble tension might confuse our understanding of how distant things, yes. So depending on how quickly the universe is expanding, the way we do distance calculations might be wrong. But so far, I haven't seen anyone successfully connect these as the same problem or the same solution or something that needs to be considered together. I think mainly because the level of precision on the Hubble tension measurements is a lot further along than the JWST measurement, which, it's early days. It only went up 2 years ago. two years ago, I think it was. So it's still very early days to talk about this, but it is very, very, very cool question. Okay, I just see two questions that I'm going to answer very quickly because we are at the 1 hour mark. Can phenomenologically emergent dark energy be a viable solution to the Hubble tension? Yeah, depends who you ask. So there's a lot of dark energy models that try to solve the Hubble tension to various levels of success. One of the most successful ones is what is known as early dark energy or new early dark energy, where you add a second period of dark energy before the current one, or dark energy emerging at a specific time in the universe and doing a specific thing. And this is something that seems to solve the Hubble tension to some degree. But then, depending on who you ask, it makes other things worse. There's actually the kind of debate in the field as to how much this early dark energy or emergent dark energy can solve the tensions or make things worse. So there are a lot of models where you can play about with dark energy to try to address the Hubble tension. And generally, I would say probably half of the solutions people have come up with involve some type of dark energy, because it's a logical one to consider, because dark energy affects the way the universe expands. So it might be related to how we measure the expansion rate of the universe. So a lot of people try to play about with dark energy to try to solve the Hubble tension to various levels of success. We're still waiting for the perfect solution, the unicorn that's going to solve all of our cosmological problems in one go. That would be fun. Maybe someday we'll get there. Can I do a stream on class on Monty Python one day? I have done, I think, twice now, where I do a stream about class, where it's interactive and it's like live demo that's run class on the spot. As always with live demos, it doesn't go as planned. So just very quickly, class is a cosmological code that you input your cosmological model, and it tells you what the CMB is going to look like, or what the amount of matter in the universe is going to look like. It's kind of one of the main codes we use to simulate 13.5 billion years of evolution of the universe. You put in your starting point and you fast forward things. And I am one of the main developers of this code, although I've been a lot less involved in it the last 2 or 3 years. But during my PhD and first postdoc, I was one of the main developers of the code. Monty Python is one that allows you to, Monty Python does the statistical analysis. Monty Python is where we build our likelihoods, which I mentioned before, are the codes that connect data and model. So what Monty Python does is it takes different data sets that you need to code into it, and it compares these different data sets to the output of class. So Monty Python will do the statistical test to tell you how likely a model is given the data that you have. Based on class, it gets the model, and then based on the different likelihoods, it gets the different data. I am also a co-developer of Monty Python, and they're two tools that we use a lot in cosmology. Doing live demos of them is fun and tricky, and I feel like it leans more into a bit too specialized for this type of stream. I've done it once or twice. It doesn't always work because it requires a lot of people to be interested in staring at a code, and I don't think everyone is overly interested in that. At some point, we built a really nice graphical interface that you press some buttons and you could actually spit out what the CMB itself would look like, and that was much more visual and fun to use. But I'm not sure if that is working anymore because it was being developed by bachelor students as a bachelor project. And I think now it's broken and hasn't been fixed in a while, which is a shame. But if we can get that working again. Did I contribute to the Monty Python name? I did not. Monty Python has existed for many years before I became involved in it. I jumped in when we switched to version 3.0. So there was version 1 that was written by one person, then it switched to version 2, and it kind of passed on to somebody else. And then we switched to version 3, and that's kind of the time when I got involved. So now I'm one of the 2 main developers, but there have been 2 or 3 other developers in the past who no longer contribute to the code. But now I am one of the 2 main developers of the code. But the name is not mine, but also it is absolutely, it does Monte Carlo simulations in Python. So we call it Monty Python. Very cool. And the code is full of Monty Python flying circus references. Monty Python references, because of course it is. Super discussion today, no lack of fun to talk about. It is indeed, I'm glad you think it's a fun discussion. I'm having fun with it. It is exactly a Monte Carlo method. It does Monte Carlo Markov chain analysis, and the code is written in Python, so we called it Monty Python, or it was called Monty Python. Great at naming things. Again, it's a theme. Monty Python, yes. Monty Python does Monte Carlo analysis. using either Metropolis Hastings, this is very technical now, using either Metropolis Hastings or nested sampling. They're both built in. There's also MC built in. There's quite a few things built in. I can think about doing a demo, not anytime soon, but at some point we can do a demo of class and MontyPython again because, I have fun with it. So that's okay. We also, as just reminded us here in the comments, we have a smartphone game that simulates cosmological stuff. And we made it as physically realistic as possible. And it's ridiculously addictive and annoying and fun to play with. It's called Dark Master. Can you become the Dark Master of the universe? We were full on dramatism here. It's available in the App Store. It's available in the Play Store. You can still download it, play about with it. So Dark Master in the App Store, in the Play Store. You'll see some cosmology info appearing. I wrote those, and it's very fun. I think it is. You play as Dark Matter, and then at some point you play as a photon trying to form the CMB. It's really fun. Check it out if you want. It's called Dark Master. It's in the App Stores. Someday it will be ported to another language, and some future grad student will wonder about the name. I feel like MontyPython is not going to leave to a different language anytime soon because Python is just exactly what we need for this type of tool. And I guess in the future, somebody wanted one in a different language, they would just directly write one in a different language. Because I feel like this type of code is something that you'd rather write from scratch than adapt from somebody else's code into a different language. Okay, I think I got through all of the questions today. Did I? Yes. Scott, as I told you before, I don't like that type of humor. I'm probably not going to watch the video you sent me. I know you keep asking me about it. I'm probably not going to watch it because it's just not my type of thing. Okay, so I think I got through all of the questions. It's been a lot of questions today. This is really fun. I feel like we went in some really fun directions with the tangent of well, not even a tangent, a long discussion of different dark matter models. We've covered some called particle physics, gravity, the different percentages in the pie chart. It's been really fun. We've had a lot of really, really cool questions today. So thank you everyone for that. It's always fun. When I turn up to these streams, there's always the big uncertainty of, are you going to have questions? Because if you don't have questions, then I have to improvise for a whole hour. And I love it when there's so many questions that we run over time because it's just great fun. And thank you. I will absolutely enjoy my YOLO do it. I'm very much going to enjoy those. I love those things. So this is probably the last cup of cosmology of this year. I'm not yet sure if there will be another one. Next week, I'm traveling. I'm really, really, really excited about it. I'm traveling on Saturday. I'm going to India. It's going to be really, really fun. So next week, no stream. The week after, I think, is Christmas Day. Or is it? Which day is Christmas Day? No, it's the 24th. Yeah, so Christmas Eve. So obviously I won't be doing a stream on Christmas Eve. And then the weekend after is New Year's Eve. So I also won't be doing a stream on New Year's Eve. I might decide to do a stream during the week of the 26th, 27th, 28th, around those dates, but I'm not yet sure. But the regular Sunday streams are on pause until January. But there might be a random one if I'm in the mood, and then I'll just announce it on Mastodon and on YouTube. General comment, as of next year, these streams will no longer be going out to Twitter. Because I've been saying this for a few months. This is coming. This is something that is going to happen at some point soon. So please do subscribe to the YouTube channel. If you're on Mastodon, you can follow me. It's DCHooper91_Cosmo. And in the new year, don't expect to see my streams on Twitter anymore. Twitter was a constant throughout the Periscope days, the Haps days, the YouTube days. But yeah, it's not very unlikely that you will see me on Twitter in the future. So make sure you follow me here on YouTube, follow me on Mastodon. That's where you'll get all of the announcements, but don't expect announcements on Twitter going forward. So I will probably see you all next year, but maybe beforehand. So I hope you will have a good Christmas period or holiday period, whether you celebrate Christmas or not. I hope you can have a break, get some rest, enjoy the end of the year. And Cosmology will be back next January with more physics, more cosmology, more cool questions. I hope to see you all then. And I hope in the meantime, you all stay safe and you all take care of each other.